Our sun is a solitary beacon in the cosmic dark, but what if it had a family of 11 other suns? This is the mind-bending reality of a duodecuple star system, a place where a dozen stars are locked in a gravitational embrace. We are about to journey through 30 of the strangest discoveries made about these cosmic marvels, revelations that challenge the very laws of physics as we know them. You will learn how planets survive under 12 suns and why these systems might be hiding invisible monsters. What does it take for a star to live its entire life surrounded by a celestial crowd? The very existence of a stable duodecuple system is the first great cosmic paradox. Think of the solar system you know, a single star holding planets in neat, predictable orbits. Now picture 12 of those stars, each a titan of gravity, all trying to share the same cosmic neighborhood. The miracle is that they do not immediately collapse into a cataclysmic firestorm. They survive through a masterfully choreographed gravitational ballet, a dance so complex it defies simple explanation. This stability comes from a strict hierarchy, a celestial pyramid scheme of orbits. At the base, you have close-knit pairs of stars, tight binary systems whirling around each other in a frantic pas de deux. These pairs then become a single unit, orbiting with another pair in a wider, slower dance. That new quadruple system then finds another partner, and the pattern repeats, building layer upon layer of gravitational relationships until you have a system of 12. It is like a multi-layered carnival ride, where each spinning cart is itself attached to a larger, spinning arm, all moving in a synchronized frenzy around a central point that itself is moving through the galaxy. This intricate structure is the only way such a crowded system can achieve a fragile, long-term peace. The gravitational pull from each level of this cosmic hierarchy balances the pulls from all the others, creating a web of forces that holds the entire chaotic arrangement together. Without this precise, layered ordering, the system would tear itself apart in a mere cosmic instant. Within this gravitational labyrinth, astronomers have made the even more baffling discovery of planets. Worlds that somehow cling to existence in a sky dominated by 12 suns. A planet here would not know the simple rhythm of day and night. Its surface would be a theater of perpetual shifting light. Multiple shadows stretch and contort, cast by a collection of suns that never all set at once. Some stars would blaze as brilliant disks, while others, farther out, would shine with the steady intensity of a full moon. The very idea of a habitable zone, that narrow band where liquid water can exist, is turned on its head. It is not a static ring around a single star, but a dynamic, shimmering shell of space that constantly warps and shifts as the stellar families swing through their grand orbits. One moment, a world might be perfectly positioned for life, bathed in gentle warmth from several stars. Then, as the dance continues, it could be pulled into a region of intense, multi-sourced heat or cast out into a deep freeze. This leads to seasons beyond our comprehension. Forget a predictable yearly cycle of spring, summer, autumn, and winter. The climate on such a world would be governed by the overlapping rhythms of its many suns. A long, stable summer might arrive when two particular binary pairs align on the same side of the planet, only to be shattered by a sudden temperature plunge as a third stellar group swings into view, its gravity subtly tugging the world into a new thermal balance. The year would be a chaotic symphony of climatic shifts, with patterns so complex they might not repeat for millennia. Life, if it could arise at all, would face a reality of endless, unpredictable change. This frantic gravitational dance creates stars that move at impossible speeds. Deep within the heart of these systems, astronomers have found pairs of stars locked in orbits so tight they defy comprehension. These inner binaries whirl around each other not in years, but in a matter of days or even mere hours. They are so close that their surfaces are practically touching, separated by a gap that is a tiny fraction of the distance between the Earth and our Sun. At such proximity, gravity does bizarre things. The immense pull from each star stretches its partner, warping both into teardrop shapes instead of perfect spheres. They are no longer two separate bodies, but a single, seething mass of connected plasma, caught in a permanent, violent embrace. This intimacy has catastrophic consequences. The stars are constantly stealing material from one another, a process known as mass transfer. Streams of superheated gas ripped from the distorted surface of one star flow relentlessly onto its companion. This creates an environment of perpetual stellar fury. The turbulent magnetic fields generated by this chaotic interaction snap and reconnect, unleashing constant, violent flares that dwarf anything our Sun could ever produce. The system bathes its inner regions in an unending storm of high-energy radiation, including intense X-rays that would instantly sterilize the surface of any planet unfortunate enough to be nearby. This makes the space around these inner binaries some of the most hostile environments in the entire galaxy, places where the very concept of a world is rendered meaningless by the unrelenting stellar violence. Far from the frantic heart of the system, a different kind of star endures its slow and solitary reign. These are the ancient, slumbering giants of the outer reaches, colossal red giants and supergiants that move on timescales almost too long to comprehend. While the inner stars complete their frantic dance in days or years, these behemoths trace their ponderous orbits over thousands of years. They are the elder statesmen of the system, glowing with a cool, deep crimson light that barely seems to notice the chaotic blaze at the system's core. Their immense gravity still binds them to the central chaos, but their experience of it is one of profound distance. A slow, stately waltz around a fireworks display they can only observe from afar. The most mind-bending possibility is that these outer giants might not be alone. Astronomers theorize they could host their own families of planets, worlds that have known only the gentle, constant light of their single, aging sun for millennia on end. Imagine a planet orbiting a red giant, a world where the sun is a vast ruby orb filling a large part of the sky. For centuries, life on such a world would experience a stable, if dim, existence. But then, a change would begin. A new, brilliant point of light would appear in the heavens, growing steadily brighter over generations. This would be the vanguard of the inner stellar cluster, beginning its long-foretold close approach. As the cluster draws nearer, the sky would become a crowded stellar metropolis. Multiple suns of different colors and intensities would rise and set in a complex, terrifyingly beautiful ballet. The gentle gravitational hand of the red giant would be challenged by the combined pull of a dozen other stars. The planet's orbit would warp and shift, pulling it unpredictably closer to or farther from its own sun. The climate, once so stable, would be thrown into utter chaos. A long ice age could be abruptly shattered by a period of intense global warming, only for the world to plunge back into a deep freeze as the stellar cluster recedes over the next 1,000 years. For any life on these outer worlds, the arrival of the inner suns would be an event of mythic, civilization-altering proportions, a periodic celestial invasion that rewrites the very rules of their existence. This gravitational balancing act is not as perfect as it first appears. When astronomers carefully track the intricate dance of all 12 stars, they find something deeply unsettling. The movements do not quite add up. The stars are whirling with a speed and force that suggests they are being pulled by something more, a vast amount of mass that remains completely invisible to our most powerful telescopes. A significant portion of the system's gravity seems to come from nothing at all. This is the mystery of the missing mass. One possible answer lies in the shadows, in the form of countless failed stars known as brown dwarfs. These are cosmic objects that were never quite able to ignite the nuclear fires in their cores. They are too massive to be called planets, yet not massive enough to become true stars. A brown dwarf is a cold, dark ember radiating only a faint residual heat. In the crowded confines of a duodecuple system, dozens, perhaps even hundreds of these dark orbs could be drifting between the brilliant suns. They would be nearly impossible to see directly, their dim glow lost in the overwhelming light of their stellar neighbors. Yet their combined gravitational pull would be immense, acting like hidden anchors that subtly shepherd the visible stars along their path. But there is an even more extreme possibility. The missing mass could be tied up in black holes. A stellar mass black hole, the grim remnant of a massive star that lived a short, violent life and then collapsed, could be lurking in the system. Its presence would be betrayed only by its gravity, an invisible knot of spacetime so dense that it tugs on everything around it. In such a complex system, a black hole would not necessarily be a destructive force. Instead, it could act as the system's gravitational keystone, its powerful pull providing a central point of stability around which the chaotic stellar dance organizes itself. These unseen dark objects, whether they are cold brown dwarfs or voracious black holes, may be the true architects of order, the hidden hands that keep a dozen suns from tearing each other apart. This stellar vampirism creates a ticking time bomb. The denser companion star does not just siphon material, it hoards it. Layer by layer, hydrogen stolen from its neighbor accumulates on the white dwarf's incredibly dense surface. This stolen atmosphere is compressed and heated under the immense gravity, building pressure in a cosmic pressure cooker with no release valve. Eventually, the base of this hydrogen layer reaches a critical temperature of millions of degrees, and nuclear fusion erupts across the entire surface of the white dwarf in a runaway chain reaction. The result is a nova, a sudden, colossal thermonuclear explosion that can blast the accumulated stolen material into space in a blinding flash. In a duodecuple system, this is not a one-time event. The vampirism continues, the cycle repeats. The white dwarf begins stealing material all over again, patiently rebuilding the fuel for its next violent outburst. This creates a recurrent nova, a star that explodes again and again, flaring to incredible brightness every few decades or centuries. But there is an even more extreme outcome. If the white dwarf accumulates so much mass that it nears a critical limit, something far more catastrophic occurs. The entire star, not just its surface, becomes unstable. In a fraction of a second, the immense pressure triggers carbon fusion in its core, leading to a runaway reaction that tears the entire star apart. This is a Type Ia supernova, one of the most energetic events in the universe. The explosion is so perfectly uniform and brilliant that it can outshine an entire galaxy. Within a crowded star system, such an event would be apocalyptic. The sheer blast of radiation and high-energy particles would scour the entire system, vaporizing any nearby planets and violently stripping the atmospheres from worlds light years away. This means that in a duodecuple system, a single, seemingly passive white dwarf can transform into a civilization-ending weapon, a testament to the fact that the greatest dangers in these cosmic families often hide in plain sight. The sheer complexity of these systems suggests they should be ancient, the final product of billions of years of slow gravitational sculpting. Yet some duodecuple families are cosmic infants. We find them blazing within stellar nurseries, vast clouds of gas and dust where new stars are still being born. This is a profound paradox. How can a structure of such intricate, multi-layered orbits assemble so quickly? The leading theory points to a violent and recent origin. Instead of a slow, peaceful gathering, these systems might be the product of a celestial car crash. Imagine two smaller, stable star clusters, each with its own internal hierarchy, drifting too close together over millions of years. Their mutual gravity would pull them into a chaotic merger. During this cosmic collision, the delicate gravitational bonds within each cluster are shattered and then rewired. Stars are thrown into wild new orbits, some ejected entirely into the void, while others are captured by the opposing cluster's gravity. In the turbulent aftermath, a new, more complex order can emerge from the chaos. the most stable configurations survive, forming the layered hierarchies we see today. It is not a slow construction, but a rapid, violent reorganization. Another possibility is the dramatic breakup of a single, incredibly massive star-forming core. If a colossal cloud of gas fragments into not just a few stars, but dozens at once, they can be born into a pre-packed family. Their initial orbits, set by the cloud's turbulent collapse, might already hint at the complex dance they will perform. Over just a few million years, a brief moment in cosmic time, gravitational interactions would refine this initial chaos into a stable, multi-tiered system. These youthful giants force us to rewrite the story of how star families are born. They prove that cosmic complexity does not always require eons to develop, that a dozen suns can find their balance not through patient evolution, but through a single, catastrophic and creative event. Even with a dozen stars, the system's balance is precarious. The gravitational dance at its core is not always a peaceful one. Close encounters between the tightly packed inner stars act as a natural slingshot. When three or more stars swing close together, their complex gravitational interplay can transfer a massive amount of energy to one of them. In a flash, that star is hurled outward, not just nudged, but violently ejected from the family at speeds that can exceed 1,000,000 miles per hour. It becomes a runaway star, a celestial fugitive cast out from its crowded home and sent on a solitary journey through the galactic void. These rogue stars are the ghostly evidence of past chaos within Duodecuple systems. Astronomers can sometimes spot these lone, high-velocity travelers, and by tracing the path of their flight backwards through the galaxy, find that their origin points directly back to one of these complex stellar families. It is a cosmic crime scene where the trajectory of the ejected star is the smoking gun, revealing a moment of immense violence that happened millions of years ago. This means every stable Duodecuple system we see today is a survivor. It has endured its own internal turmoil, expelling its most disruptive members to achieve the fragile peace we now observe. The stars themselves hold chemical secrets written in the light they emit. Astronomers analyzing the atmospheres of stars within Duodecuple systems have found bizarre and inconsistent chemical fingerprints. While most solitary stars in our galactic neighborhood share a similar cosmic recipe, primarily hydrogen and helium with a small, predictable dash of heavier elements, these stellar families break all the rules. Some members show a startling poverty of metals, the term astronomers use for any element heavier than helium. They are cosmic purists, relics from an earlier time in the universe when such heavy elements were scarce. Yet, right beside them in the same gravitational dance, other stars gleam with a surprising metallic richness. They are contaminated, their atmospheres brimming with elements like iron, carbon, and oxygen far beyond normal levels. This stark chemical divide within a single family points to a violent shared history. The most likely explanation is a supernova that occurred within the system long ago. When a massive star reaches the end of its life and explodes, it becomes a cosmic forge, creating a vast cloud of heavy elements and blasting them outward at incredible speeds. In a crowded system, this newly forged material does not simply vanish into the void. It slams into the surrounding gas and dust, including the cocoons of gas that are still coalescing into sibling stars. Those young stars would form from this polluted material, incorporating the ashes of their dead sibling directly into their very makeup from birth. This creates a unique chemical family where the stellar generations are linked not just by gravity, but by a literal inheritance of elemental stardust. One star's catastrophic death becomes the raw material for its brothers and sisters, a permanent chemical record of a past apocalypse that forever binds the family together. This simultaneous birth of a dozen stars presents a fundamental puzzle for astronomers. Our standard models of star formation work beautifully for single stars like our Sun, or even for small binary pairs. A lone cloud of gas and dust collapses under its own gravity, spinning faster as it shrinks, eventually forming a star at the center, perhaps with a leftover disk that might become planets. But this process cannot simply be scaled up to create 12 stars at once. The chaos would be overwhelming. You would expect such a large, collapsing cloud to fragment into a few large clumps, not a precise dozen stable seeds. The existence of these systems forces us to rewrite the textbooks on stellar birth. The leading answer lies in a process known as turbulent core collapse, but on a truly monstrous scale. Imagine a single, colossal cloud of gas, not just a few times more massive than the one that birthed our sun, but thousands of times more massive. This cloud is not calm and serene. It is a raging, chaotic storm of internal motion, with supersonic winds and rippling shockwaves crisscrossing its entire volume. This internal turbulence acts like a cosmic blender, churning the cloud and preventing it from collapsing into just one or two massive stars. Instead, the turbulent motions create a vast network of dense knots and filaments. Each of these knots becomes a gravitational anchor, a seed around which a star can form. In the right conditions, this process can spawn an entire litter of stellar siblings all at once. The intricate dance of their orbits is set from the very beginning, imprinted by the complex, swirling motions of that primordial gas cloud. We are only beginning to understand how this initial chaos can settle into the stable, hierarchical order we see today, a cosmic mystery written in the very first moments of a star system's life. This stellar graveyard is more than a silent relic. It is a dynamic and often violent part of the system's present. The dense environment of a duodecuple system acts like a pressure cooker for stellar evolution, dramatically speeding up the life and death of its members. Close gravitational encounters can strip a star of its outer layers prematurely, exposing its core and effectively giving it a head start on the path to becoming a white dwarf. More dramatically, direct collisions between stars, while rare in the wider galaxy, become a real possibility in this crowded neighborhood. When two stars merge, they can create a single, bizarrely massive star that burns through its fuel at a ferocious rate, living a short, spectacular life before exploding as a supernova and leaving behind an ultra-dense neutron star. This accelerated life cycle means these systems often contain a museum of stellar corpses, a collection of white dwarfs, neutron stars, and pulsars all orbiting peacefully alongside their still shining siblings. The most startling of these remnants is the pulsar. A pulsar is a rapidly spinning neutron star, the collapsed core of a massive star that exploded. It is a city-sized object with the mass of our entire sun, compressed into an unimaginable density. As it spins, it beams intense radiation from its magnetic poles, and if those beams sweep across Earth, we detect a regular, repeating pulse of radio waves. Now picture such an object within a duodecuple system. Its precise, metronome-like tick would cut through the gravitational chaos, a stark, rhythmic counterpoint to the unpredictable flares and shifting orbits of the living stars. For any hypothetical observer within that system, this pulsar would be a cosmic lighthouse, its steady flash a rare point of certainty in a sky of perpetual stellar turmoil, a beacon from a dead star that somehow orders the chaos of the living. Yet another layer of order emerges from this apparent chaos, a celestial configuration so clever it seems like a mathematical trick. Astronomers have found stars within these systems acting as gravitational shadows, occupying the stable parking spots known as Lagrange points. In our own solar system, we see this with the Trojan asteroids, which lead and follow Jupiter in its orbit around the Sun, forever trapped in a gravitational sweet spot. Now scale that idea up to a star trailing or leading another star. Within a duodecuple system, a pair of tightly bound binary stars creates a complex gravitational landscape as it orbits. In this landscape, there are specific points where the pull from the two stars and the centrifugal force of motion perfectly balance out. A third star of just the right mass can slip into one of these points and be held there, forever leading or following the binary pair in their grand dance around the system's center. It is a cosmic game of follow the leader on an epic scale. This Trojan star is not merely a close companion, it is a co-orbital partner, locked into a precise celestial formation that requires almost no energy to maintain. This discovery reveals that these complex systems are not held together by brute gravitational force alone, but by an almost artistic application of orbital mechanics. The system finds every possible loophole in the laws of physics to maintain its fragile peace. How many of these Trojan pairs might be hiding within the stellar crowd, their synchronized motion adding a hidden rhythm to the system's frantic beat? The gravitational chaos of 12 stars reshapes the very cradle of planets. Before a world can even form, it begins as a swirling disk of gas and dust orbiting a young star. This protoplanetary disk is the raw material for future solar systems, a serene nursery where dust grains gently collide and stick together, slowly building pebbles, then rocks, and eventually planets. But in a duodecuple system, this nursery is thrown into a state of perpetual pandemonium. The combined gravitational pull from a dozen suns acts like a team of invisible, colossal hands, constantly kneading and pulling at these fragile disks. They are stretched, warped, and torn into bizarre, distorted shapes. Some are truncated, their outer edges sheared off completely, robbed of the material needed to form giant planets like Jupiter. Others are sculpted into intricate rings and spirals, patterns carved not by the gentle hand of a single star, but by the violent tug of war between many. Simulations reveal this process is brutally efficient. A disk that would have stretched for billions of miles around a single, solitary star can be compressed into a tight, frantic whirlpool, its material funneled inward or flung out into the void. The gentle dance of dust grains is replaced by a high-speed demolition derby. Collisions are not gentle mergers, but violent impacts that shatter fledgling worlds back into dust. The stable, quiet zones where planets like Earth could slowly assemble over millions of years are erased by the relentless gravitational stirring. Any planet that does manage to form in this environment is likely to be a strange and exotic survivor. Imagine a world born from a ring of debris, its entire orbit defined by a narrow band of material that somehow resisted the stellar chaos. Or a planet flung into a wildly eccentric path, a celestial nomad that experiences extremes of heat and cold as it dives close to one star and then swings out toward another. The very process that gives rise to planets in our solar system becomes a violent, turbulent filter in a system of 12 suns, one that likely produces only the most resilient and bizarre of worlds. This cosmic choreography extends to the very spins of the stars themselves. In a handful of these complex systems, astronomers have noticed something that defies the odds. Multiple stars are not just dancing around each other, they are spinning in the same direction, as if they were all twirling on identically aligned axes. In a chaotic environment where stars are born from a turbulent cloud, you would expect a random jumble of rotations, some stars spinning upright, others sideways, and still others tilted at every conceivable angle. Finding this kind of family-wide alignment is like walking into a room full of tops and discovering they are all spinning in perfect unison. This is not a coincidence. It is a fossilized clue, a direct imprint from the system's birth. The original, colossal gas cloud that collapsed to form these 12 stars must have possessed an immense, organized sense of rotation. Think of it as a single, coherent spin that permeated the entire cloud. As the cloud fragmented into dozens of individual stellar seeds, each fragment carried with it a piece of that original momentum, like droplets of water flying off a spinning bicycle wheel. Each droplet inherits the wheel's direction of spin, the most likely force that could orchestrate such uniformity on such a grand scale is a powerful magnetic field. These invisible lines of force woven through the primordial gas can act like cosmic guide wires, channeling the cloud's collapse and enforcing order on the chaos. They ensure that when the stellar siblings are born, they all remember their shared origin, their spins locked in a silent, coordinated ballet that has lasted for billions of years. These stellar dances are not silent. Every tight orbit, every close encounter between these massive stars sends vibrations racing through the very fabric of the universe. Duodecuple systems are gravitational wave factories, constantly generating the faintest ripples in space-time. These ripples are not made of light or matter, but are literal waves of distortion traveling outward at the speed of light, a direct consequence of the immense accelerating masses. For now, most of these waves are too faint for our current observatories to detect, but the next generation of gravitational wave telescopes, designed to listen to the cosmos from space, will tune directly into this cosmic symphony. Think of it this way: until now, we have only been able to watch these systems like observing a silent movie of a complex dance. We can see the stars move, but we cannot hear the music that guides their steps. Gravitational waves are that music. They carry information that light simply cannot. By listening to them, we will hear the precise orbital dynamics of the innermost binaries, especially those involving the densest stellar corpses like neutron stars and black holes. We could detect the subtle, inaudible hum of a black hole orbiting a neutron star, or the rising crescendo of two white dwarfs spiraling ever closer. This new sense will allow us to probe the very heart of these systems, to measure the masses and spins of objects that are otherwise completely invisible, revealing the hidden architects of this gravitational ballet. We are on the verge of not just watching the dance of a dozen suns, but of finally hearing its rhythm. This stellar chorus can turn into a screaming superchorus. When one of these flare stars erupts, it does not happen in isolation. The blast of radiation and the cloud of charged particles it hurls into space does not simply fly off into the void. It slams directly into the complex magnetic webs of its closest stellar neighbors. Think of it like a domino effect, but with the power of a solar flare on every single domino. A colossal flare on one star sends a shockwave ripping through the shared space of the system. This wave of energy and magnetic disturbance can violently compress the magnetic fields of adjacent stars, forcing them to snap and reconfigure in a process called magnetic reconnection. This reconnection is the trigger for a stellar flare, so one star's violent outburst can directly induce another star to erupt. That second flare then triggers a third, and the chain reaction spreads. The result is a superchorus, a coordinated symphony of stellar fury where half a dozen suns might erupt in sequence over a matter of days or even hours. The entire inner region of the system would be scoured by a rolling storm of X-rays and ultraviolet radiation, a series of plasma tsunamis crashing through the cosmic neighborhood. For any hypothetical planet, this would be an extinction-level event on repeat. Just as the atmosphere might begin to recover from one radiation blast, the next star in the chorus would ignite, delivering another lethal dose. The planetary surface would be sterilized over and over again, making the inner realms of these systems not just hostile but perpetually apocalyptic. These stellar fireworks leave a permanent mark on the cosmos, sculpting the space around them into breathtaking structures. The combined stellar winds and radiation pressure from 12 stars act like a team of cosmic artists, carving the surrounding clouds of gas and dust into shapes of impossible complexity. We see vast, shimmering bubbles expanding outward, their surfaces rippling with the conflicting pushes and pulls from multiple stellar sources. We observe intricate, spiral-patterned nebulae like cosmic fingerprints pressed into the interstellar medium, each swirl and arc a direct record of a gravitational tug-of-war. These are not the serene, symmetrical nebulae born from a single dying star. They are chaotic, dynamic sculptures, a visible echo of the frenzy happening at their heart. The sheer force involved is staggering. the fastest stellar winds blasting out from the most massive stars at millions of miles per hour slam into slower moving material ejected by cooler, older giants. This collision creates shock waves that heat the gas to incandescence, making it glow with an unearthly light. Dust grains are not simply drifting, they are caught in a frantic whirlpool, some being blasted away into the darkness while others are herded into dense, dark lanes that twist through the nebula. This ongoing construction project acts as a real-time laboratory, showing us how the raw energy of a star system can physically reshape its corner of the galaxy, leaving behind a monument to its own turbulent life. Keeping track of this celestial family tree is a logistical nightmare for the astronomers who study them. In our own solar system, we have simple, elegant names for planets, a tradition stretching back to antiquity. But how do you name a system with 12 suns? The standard convention of giving a star a single name, like Sirius or Vega, collapses completely. Instead, these systems are often assigned a dry catalog number followed by a confusing string of letters. The brightest star might be designated component A. Its close binary partner becomes component B, but then that entire pair as a unit orbits with another pair which would be components C and D. That new quadruple system then gets a new letter as it dances with another star. You quickly end up with a designation that looks less like a name and more like a complex algebraic equation. It is a system built for computers, not for storytellers. The true challenge, however, is not just in the naming but in the tracking. Over years of observation, astronomers must meticulously follow the movements of each component, ensuring that the star they identified as component G a decade ago is the same one they are looking at today. With orbits overlapping and stars whirling in and out of view from our perspective, this becomes a monumental game of cosmic bookkeeping. A single misidentification could throw off the entire gravitational model of the system, turning a carefully choreographed dance into an unsolvable mess. It is a humbling reminder that for all their grandeur, these dozen-sun systems present a very human problem, one of organization and patience, forcing us to invent new languages just to describe their breathtaking complexity. These forbidden orbital zones are the system's gravitational dead ends. We see a similar principle at work right here in our own solar system, within the asteroid belt between Mars and Jupiter. The immense gravity of Jupiter creates distinct gaps in the belt, regions where an asteroid's orbital period would be a simple fraction of Jupiter's own, like 1/2 or 1/3. An asteroid in such a resonant orbit receives a repeated, rhythmic tug from the giant planet. Over millions of years, these tiny nudges add up, pulling the asteroid out of its original path and clearing a gap in the belt. Now take that concept and amplify it with the gravitational chaos of 12 stars. In a duodecuple system, you do not have one Jupiter creating a few simple resonances. You have a dozen gravitational powerhouses, each with its own complex orbital rhythm. Their overlapping pulls create a web of resonances so intricate it resembles a tangled knot of gravitational strings. Any region of space where these resonances intersect becomes a zone of pure instability. A planet or even a smaller star trying to orbit in one of these zones would find itself caught in a gravitational crossfire. The competing tugs from multiple stars would not be gentle nudges but violent, contradictory forces. One moment, a star's gravity pulls it inward. The next, a different star's influence yanks it outward. Its orbit would be stretched and warped beyond recognition, a chaotic trajectory with no hope of long-term stability. The object is swiftly ejected, either flung out of the system entirely or sent on a collision course with another body. The result is a cosmic architecture punctuated by emptiness. These are not random voids, but precisely calculated gaps, the ghostly imprint of gravitational mathematics made visible. They are the places where the music of the spheres falls silent, where the complex harmonies of 12 suns create pockets of perfect dissonance that nothing can survive. The influence of a duodecuple system does not end at its own gravitational borders. Its power radiates outward, shaping the destiny of its entire galactic neighborhood. These stellar families act as colossal engines of galactic evolution, their violent lives and deaths dictating the fate of countless other stars yet to be born. The primary tool for this cosmic control is intense radiation. With a dozen suns, many of them massive and hot, the system floods its surroundings with a relentless blizzard of ultraviolet light. This high-energy radiation is a potent cosmic heater. It slams into the vast, cold clouds of hydrogen gas that drift between the stars, the very raw material for future solar systems. The UV radiation does not gently warm this gas, it violently ionizes it, stripping electrons from atoms and causing the cloud to heat up and expand. This heating can prevent the cloud from collapsing under its own gravity, effectively shutting down the star formation process before it can even begin. In this way, a duodecuple system can carve out a vast, sterile bubble around itself, a region where no new stars are permitted to ignite. It becomes a galactic quarantine zone, its radiant fury keeping the cosmic nursery empty for light years in every direction. Yet the story is not so simple. The same system can also be a catalyst for creation. When one of its most massive members ends its life in a supernova, the explosion does more than just forge heavy elements. The shockwave from the blast, a sphere of expanding gas and energy moving at a fraction of the speed of light, can plow into a neighboring gas cloud like a cosmic bulldozer. This immense pressure compresses the gas, triggering turbulent collapses within the cloud that would not have happened otherwise. The supernova shockwave crushes the gas, creating dense, fertile pockets that rapidly collapse to form a new generation of stars. So, the very same system that uses radiation to prevent star formation in one area can, through a supernova, trigger a burst of new star birth in another. It is both a destroyer of potential and a midwife to new suns, its influence a paradox of creation and destruction woven into the fabric of the galaxy. These sprawling stellar families are slowly unraveling at the edges, stretching far beyond the brilliant chaos of the central suns. Astronomers have detected long, ghostly rivers of light. These are tidal tails, vast streams of stars that have been gently pulled from the system's gravitational grip over billions of years. The process is a slow and patient one, driven by the immense tide of our entire galaxy. As the duodecuple system travels along its galactic orbit, it does not move in perfect isolation. The differential gravity of the galaxy, stronger on the side closer to the galactic center and weaker on the far side, creates a stretching force. This galactic tide acts like a persistent hand, constantly plucking at the most loosely bound stars in the system's outer layers. One by one, these stars are persuaded to leave, each departure a tiny theft of mass from the stellar family. They do not fly away at random. Instead, they drift into two distinct streams, one leading ahead of the system in its orbit and one trailing behind, painting twin arcs of escape across the darkness. These streams are more than just beautiful relics. They are a form of cosmic archaeology, a living record of the system's long and turbulent life. By mapping the precise paths and densities of these stellar rivers, astronomers can read the history written in their light. The rate at which stars are being lost tells us about the system's current mass and its binding strength. The specific stars found in the streams reveal which members were most vulnerable to escape, often the lighter, cooler stars that once inhabited the system's outer fringes. Most importantly, the shape and structure of the tails can betray past traumatic events. A kink or a bend in the stream might mark a moment, billions of years ago, when the entire system had a close encounter with a massive interstellar cloud or another star cluster, a gravitational shock that accelerated the unraveling process. These faint trails of light are the system's own autobiography, a story of gradual dissipation and forgotten members written across the void. A civilization born within a duodecuple system would see the cosmos through a completely different lens. Their entire reality is a celestial clockwork of unparalleled complexity. For them, the rhythmic orbits of their 12 suns would form the ultimate timepiece. The frantic, days-long dance of the inner binaries could mark their hours. The slower, years-long circuits of the mid-level pairs could define their years. And the majestic, millennia-long orbits of the outer giants would chart the epic, civilization-spanning epochs of their history. Their calendar would be a multi-layered symphony of time, its patterns so intricate they might spend generations just to predict the next great alignment of all their stars. This constant, visible clockwork in the sky would make them master astronomers from the very start, their understanding of orbital mechanics born not from theory, but from daily, inescapable observation. Navigation between these stars would be as fundamental to them as sailing between continents is to us. With so many brilliant destinations so close, relatively speaking, the idea of a lonely, generations-long voyage to a single, distant sun would seem absurd. Their concept of a solar system and interstellar space would be blurred beyond recognition. A journey from a world orbiting one star to a planet around another might be no more daunting than a trip from Earth to Jupiter is in our own system. Launching a probe to a neighboring sun would be an ambitious but routine interplanetary mission. Their spacecraft would not need to aim for a faint point of light in an empty void. Instead, they would plot complex gravitational slingshots through a crowded sky, using the dance of the stars themselves as a highway. A voyage might involve swinging close to a binary pair to gain a speed boost, then coasting toward the warm glow of a red giant, all while navigating the gravitational tides of several other suns along the way. This redefines the very meaning of space travel. For such a culture, exploration is not a lonely leap into the unknown, but a constant process of mapping the intricate connections within their own vast multi-stellar home. Their first messages to the cosmos would likely not be a simple drawing or a sequence of prime numbers. The most natural language for them to use would be the language of orbits. They might transmit the precise timing of their stars' eclipses, or the complex harmonic ratios of their orbital periods, a mathematical signature that screams of their origins in a system of 12. To them, this would be the universal constant, the most beautiful and fundamental expression of their existence. Finding such a signal would be our greatest clue that we are not just hearing from another world, but from an entirely different kind of cosmic neighborhood. This gravitational resilience extends to the very cradles of new worlds. Against all odds, astronomers have found the faint, telltale signatures of stable disks of gas and dust orbiting individual stars within these chaotic systems. The existence of such serene, structured nurseries amidst a stellar riot seems to defy all logic. How can a delicate disk, a structure easily shredded by a single passing star, survive the relentless pull of 11 others? The answer lies in a clever cosmic loophole. Many of these disks are not orbiting a solitary star, but a pair of stars locked in an incredibly tight embrace. From the perspective of the swirling dust and gas, this frantic binary is not two separate gravitational sources. It behaves as a single, combined mass, a gravitational point around which a stable disk can peacefully form. The chaos is not gone, but it is pushed to a distance. The disk orbits this tight binary pair as if it were one star, largely oblivious to the gravitational storms raging just outside its borders. This discovery completely reimagines the potential for planets in these systems. It opens the door to worlds that are born into a double sky, genuine Tatooine-like planets that orbit two suns. Imagine a young planet forming in such a disk. Its primary view would be of two brilliant suns, often so close together they appear as a single, elongated source of light, dancing around each other in a frantic, daily rhythm. These twin suns would rise and set together, casting complex, ever-shifting shadows. Yet, this is only the immediate family. Looking beyond this intimate pair, the rest of the sky would be a crowded stellar metropolis. The other 10 suns would gleam as impossibly bright stars, some steady points of light, others visibly moving over periods of weeks or years. Their combined light would turn night into a perpetual, multi-hued twilight, and their gravity would provide a constant, subtle tug on the entire binary planet system. A year on this world would be a layered experience, governed by its orbit around the central binary, but constantly modulated by the distant, rhythmic pulls of its other stellar neighbors. The possibility of life here becomes a question of gravitational fortitude, of a world finding a sheltered harbor within a hurricane of suns. The sky above such a world would be an artist's palette gone mad. Instead of a single, dominant source of light, the heavens would be filled with a collection of suns, each burning with its own distinct color and intensity. A brilliant blue O-type star, tens of thousands of degrees hotter than our sun, would pour out a harsh actinic glare. Its light would be balanced by the gentle, familiar yellow of a G-type star like our own, and further softened by the deep, ruddy glow of a cool red dwarf. To complete the spectacle, a bloated red giant might hang in the sky like a colossal, smoldering ember. The resulting light on the planet's surface would not be a simple blend into white, but a perpetually shifting hue, a unique color temperature that changes with the orbital dance. One moment, the combined light might have a cool, bluish tint as the O-type star dominates the sky. Hours later, as that star sets and the red giant rises, the entire landscape would be bathed in a warm, orange-amber twilight. There is no true night, only an eternal, multicolored dusk where shadows are not merely dark, but tinged with the colors of the absent suns. This constant, shifting light would dictate the rhythm of life itself, a visual symphony composed by the movements of a dozen different conductors. This family portrait holds a deep and puzzling secret. While most of the stars share a striking chemical resemblance, a few stand out as cosmic strangers. Their atmospheric composition tells a story of a different origin, one of solitude rather than a crowded birth. They are the only children in a family of 12, their very atoms whispering that they were not born here. The most likely explanation is a story of cosmic adoption. Billions of years ago, as this stellar family wandered the galaxy, its immense gravity may have acted like a net, snatching a lone, passing star from a disrupted cluster or even a tiny, cannibalized dwarf galaxy. This captured star was then pulled into the complex dance, becoming a permanent, if adopted, member of the family. This adds a profound layer of drama to the system's history. It means the bonds holding these suns together are not always the bonds of blood, forged in a single fiery nursery. Some are the bonds of circumstance, ties created by galactic chance and gravitational fate. One of these adopted stars might be an ancient, metal-poor relic from the early universe, a pristine fossil captured by its more modern, chemically enriched siblings. Its presence is a living piece of cosmic archaeology, a preserved sample of a time long past, now trapped in an endless waltz with stars that represent a much later chapter in galactic history. This discovery forces us to ask what truly defines a family of stars. Is it a shared birth or simply a shared destiny, a future forever intertwined by the unyielding hand of gravity? A star's fate is not its own in this cosmic crowd. The simple, solitary life of a star like our sun, burning steadily for billions of years on its own private fuel reserve, is an impossible dream here. Instead, the constant gravitational intimacy forces stars to live borrowed, extended, or tragically shortened lives. The most dramatic alteration comes from stellar vampirism, where one star strips the outer layers of hydrogen from its companion. For the star being robbed, this is a death sentence, prematurely exposing its core and cutting its life short. But for the thief, it is a fountain of youth. This stolen hydrogen piles onto its surface, acting as a fresh fuel supply that reignites its nuclear fires with renewed vigor. An aging star on the verge of cooling down is suddenly transformed back into a vibrant, hot blue youngster, its lifespan extended by hundreds of millions of years. It is a cosmic paradox where one star's longevity is purchased with the lifeblood of another. Yet this rejuvenation is a turbulent, unstable process. The transferred hydrogen does not burn steadily but often in violent, runaway bursts, turning the star into a recurrent nova and creating a beacon of unpredictable fury within the system. The gravitational embrace does more than just transfer mass, it also transfers motion. The same tidal forces that warp stars into teardrop shapes also act as a powerful spin-up mechanism. A star that would naturally rotate once every few weeks can be whipped into a frantic spin, completing a full rotation in a matter of hours. This rapid rotation has a profound consequence. It dramatically strengthens the star's internal magnetic dynamo. The result is a star gripped by magnetic fury, its surface beset by colossal starspots and rent by solar flares thousands of times more powerful than any our Sun produces. This magnetic activity acts like an engine running at redline, churning the star's interior and forcing it to burn its core hydrogen fuel at a profligate rate. While a solitary star of the same mass might shine steadily for 10 billion years, a spun-up star in a duodecuple system could exhaust its fuel in just a few billion, living a brilliant but tragically short life. Its destiny is to die young and violently, leaving behind a dense stellar corpse like a neutron star or a white dwarf, a silent testament to the gravitational forces that rushed it to its end. In this celestial family, no star is an island. Their lives, their deaths, and the very pace at which they burn are all dictated by the relentless, intimate dance of a dozen suns. This search for ultimate stability pushes astrophysics to its mathematical limits. Scientists are running countless computer simulations, searching for the one perfect arrangement that could allow a dozen stars to dance together for the entire lifetime of the universe. The results are strangely beautiful. Certain symmetrical configurations, like cosmic nesting dolls, emerge from the digital chaos as the most durable. One model arranges the stars in a pattern of nested triangles, with pairs of stars forming the points of smaller triangles that themselves trace out the corners of a larger, grander triangle. Another proposes a structure based on interlocking squares, a celestial cube where each face is governed by a stable binary pair. These geometric patterns are not random. They represent points of perfect gravitational balance, where the pulls and pushes from every star cancel each other out in a state of harmonious equilibrium. It is the orbital equivalent of a perfectly balanced mobile, where every element is in motion, yet the entire structure remains poised and steady. Theoretically, a system locked into one of these perfect shapes could survive for tens of billions of years with minimal disruption, a near-eternal monument to celestial order. Finding such a perfect system in the real world, however, is the ultimate cosmic treasure hunt. Astronomers are now sifting through the data on every known multiple star system, comparing their messy, real-world orbits to these pristine theoretical ideals. They are looking for a system where the angles between orbits are just right, where the mass ratios of the stars create a perfect harmony, and where the orbital periods resonate in clean, mathematical ratios. A real system matching a perfect model would be more than just a curiosity. It would be a laboratory for testing the fundamental laws of gravity itself, a place to see if nature, in its most complex stellar families, truly prefers the elegant solutions of pure mathematics. The discovery of such a system would suggest that the universe has a hidden preference for order, even within its most spectacularly chaotic creations. The rhythmic heartbeat of a pulsar, that perfect metronome of the cosmos, becomes a chaotic stutter in a duodecuple star system. Radio astronomers listening to these signals face a unique form of madness. They are tuning into a lighthouse whose beam is being shaken by a dozen different hands. The pulsar's incredibly regular radio pulses, which in empty space would be a model of precision, are now warped and twisted by the complex gravitational field it moves through. Each of its stellar companions tugs on the fabric of spacetime around the pulsar, subtly altering the path its radio signals must travel to reach us. The pulse we receive is not a clean tick, but a distorted echo, its timing advanced or delayed by the pulsar's frantic orbital dance around multiple centers of gravity at once. Untangling this signal is like trying to identify a single, pure musical note from a recording of a full orchestra playing in a hall with wildly distorted acoustics. It is a computational nightmare that requires sifting through mountains of noisy data, searching for the hidden, perfect rhythm buried beneath layers of gravitational interference. Yet, for those who succeed, the reward is beyond measure. This very distortion is the key to unlocking the system's deepest secrets. By meticulously modeling every delay and advance in the pulsar's signal, astronomers can perform a feat of cosmic accounting. They can weigh the entire system. The precise amount a pulse is delayed tells you the exact strength of the gravitational pull that caused it, which in turn reveals the mass of the star doing the pulling. A pulsar's twisted signal becomes a hypersensitive scale, allowing scientists to measure the mass of invisible brown dwarfs, to confirm the presence of stellar black holes, and to chart the gravitational influence of every single star in the chaotic family. This single, confused radio beacon provides a more precise map of the system's mass distribution than centuries of visual observation ever could. The strangest of these stellar families are not where you would expect to find them. They drift in the profound emptiness of the galactic halo, far above the bright, star-filled disk of the Milky Way. This is a cosmic desert, a vast and lonely space where the gas and dust needed to create new stars is almost non-existent. Finding a duodecuple system here is like discovering a bustling metropolis in the middle of an uninhabited ocean. Its presence is a profound contradiction, a cosmic crime scene with no obvious perpetrator. The solution to this mystery lies in galactic archaeology. These halo wanderers are not native to our galaxy. They are the surviving cores of ancient dwarf galaxies, small satellite systems that were torn apart and consumed by the immense gravity of the Milky Way billions of years ago. In that violent act of galactic cannibalism, most of the dwarf galaxy's stars were scattered into long, dissolving streams. But the most tightly bound structures, the complex stellar families with their intricate gravitational knots, held together. They survived the tidal forces of the merger intact, becoming orphaned fossils adrift in a new galactic home. Their chemical fingerprints confirm this epic history. The stars within these systems often possess a uniquely primitive composition, with a severe lack of metals compared to stars born in the rich environment of the Milky Way's disk. They are relics from the early universe, preserved in the time capsule of their compact structure. Each one is a ghostly ambassador from a galaxy that no longer exists, a silent testament to the violent, hierarchical way in which giant galaxies like our own are built. They are living proof that our Milky Way has a past written in stellar blood, a history of conquest whose only remaining witnesses are these 12 sun systems wandering the darkness. The most massive duodecuple systems face an ending as spectacular as their beginning. All that complex gravitational energy, the constant pushing and pulling between a dozen suns, must eventually be paid back. Computer models tracing their ultimate fate reveal a terrifying final act, a gravitational debt settled in fire and collapse. The relentless, close-quarter dances that have defined their existence for billions of years sow the seeds of their own destruction. Over immense timescales, these intricate orbits slowly decay. The gravitational tugs that once provided stability begin to act as a brake, sapping orbital energy and drawing the most massive inner stars ever closer. They spiral inward, their dance accelerating from a stately waltz to a frantic final plunge. When stars of such immense mass collide, it is not a simple merger. It is a catastrophic fusing of stellar furnaces. Two massive stars slam together, their outer layers erupting in a titanic blast of light and plasma. But their cores, impossibly dense, do not explode. They sink into one another, merging into a single, monstrous new star. This newborn behemoth is unstable from birth, a bloated leviathan burning through its nuclear fuel at a frantic, suicidal rate. It might live for only a few million more years, a brief, brilliant flash in the cosmic dark, but the process does not stop there. This newly merged superstar now possesses an even stronger gravitational pull, acting as a vacuum cleaner in the heart of the system. It begins to cannibalize its remaining siblings, drawing in another massive star and then another. Each collision adds more mass, building up an object of staggering proportions. The final product of this stellar consolidation could be a star hundreds of times more massive than our Sun. Under such incredible weight, not even the fierce fires of nuclear fusion can hold it up. The core succumbs to its own gravity, collapsing past the point of a neutron star, past any known stable state. It falls endlessly in on itself, birthing a black hole of a class we rarely see, an intermediate mass black hole with the weight of thousands of suns. This is the system's final, grim metamorphosis, a celestial family consumed to create a single dark heart. In the most extreme simulations, this process does not end. The black hole continues to feed, growing with each stellar capture until it reaches a scale that defies belief. It becomes the seed for a future supermassive black hole, the very kind that lurks at the center of galaxies. A monster born not from a primordial cloud, but from the cannibalized remains of its own stellar kin. The beautiful, chaotic dance of a dozen suns ultimately writes its own final chapter, not in light, but in absolute darkness, transforming a symphony of stars into a silent, gravitational tomb. From the ghostly trails of tidal tales to the ticking time bomb of stellar vampirism, we have journeyed through 30 revelations that twist our understanding of the cosmos. Duodecuple star systems are far more than astronomical curiosities. They are the ultimate natural laboratories, cosmic crucibles where the fundamental laws of gravity and stellar evolution are pushed to their absolute limits. In their chaotic orbits and violent interactions, we see a grand experiment playing out on a scale we can barely comprehend, forcing us to rewrite the story of how stars are born, live, and die. They challenge our definitions of stability, habitability, and even family, proving that the universe's greatest dramas unfold not in solitude, but in the complex, beautiful, and terrifying embrace of a dozen suns. So we turn the question to you: which of these strange discoveries captured your imagination the most? Was it the hidden black holes acting as gravitational keystones, the planets enduring a sky of perpetual twilight, or the stellar runaways cast out into the void? Let us know in the comments below and subscribe to continue exploring the universe's greatest mysteries with us.